Well, it's a great pleasure to welcome Sumati Surya to give today's DIAS Zoom seminar. She's going to tell us about what is a quantum causal set, and she's speaking to us from you're in Bangalore or Bangalore?
Yes,
and
Bangalore.
You are not actually in your office in the Raman Institute, but such is life at the moment. So thank you very much for agreeing to give this seminar, and we're interested to learn the latest on quantum causal sets.
Thanks, Dindru. And the title of my talk is a bit provocative, and I wish I had the answer to it. But the simple answer to what is a quantum causal set is we don't yet know. Okay. But the purpose of this talk is to talk about how we're trying to get to understand what we mean by quantum causal sets. And this is the outline. Dindru suggested that I remind people or tell people what the causal set hypothesis is. This is sort of the mandatory few slides that we always have to give for any talk. And then I will talk about two approaches to quantization of causal set theory. The first is starting with the causal set partition function, which might seem the most natural thing from a field theory perspective. And then also talk about what is this sort of sequential growth paradigm where there's a growth paradigm for causal sets, which is considered to be more fundamental, and how to make a quantum theory of that growth paradigm. This is recent work. I will talk about recent work with Stav Zalel, who is a student of Faye Dowker. She just defended. That'll be the work on quantum sequential growth, as well as some work with students of mine, Anupanand Singh and Abhishek Mathur, on the causal set partition function, and more recently, work with Peter and Steve Carlip, which is still ongoing work. There is also a slide which is work done with various collaborators, including Lisa and Dindru and Will, but I will not talk about those models extensively, but I'll just sort of briefly comment on them. So these are my first few slides on causal sets, and the motivation for causal set theory comes from the fact that there is an object called the causal structure poset associated with every causal spacetime. And that poset, it's a partially ordered set, so it's got an order relation between the events, which is acyclic and transitive, and the ordering is a causal ordering. That is, X precedes Y means that X can be causally related to Y, it can send a causal signal to Y. And what's very important in this is that the causal structure poset is not present in any other signature spacetime. So if I have a spacetime, of course, if I have Riemannian space, there are no light cones, so I don't have a causal structure. But also if I have a minus, minus, plus, plus signature, then it's like having two time directions. And as you can see from this diagram, it's kind of obvious that there's no ordering that's possible. So this causal structure poset is a stamp that you have a Lorentzian causal spacetime. So the other thing you notice about it is that under conformal transformations, causal relations do not change. So if X precedes Y in one spacetime and you do a conformal transformation, it's still true. So the light cone structure is invariant. So the question that people began to ask a while ago was, well, what happens if you have two causal structure posets from two different spacetimes and they're the same? Can you say something on the reverse? So can you say that their spacetimes that they've come from are actually conformally related? And the answer to that is yes. And there's this celebrated theorem due to Hawking, King, McCarthy, and Malamud, that if you have a future and past distinguishing spacetime, which is a particular causality condition that makes sure that each element is sort of distinguishable from each event, is distinguishable from any other event based on its causal futures and pasts. And this theorem basically says that, yes, if there is such a bijection between the posets, the causal structure posets, then these two spacetimes are related by a conformal transformation. So it gives us a very different way of thinking about spacetime, just from this purely Lorentzian geometry perspective, which is that it's a causal structure poset plus a conformal factor, which is basically a local volume element. And that sort of, if you want to write an equation, you basically say, well, you have the spacetime is equal to the causal structure poset plus this scalar. And as you can tell, this means that there's a lot of information that's actually there in the causal structure poset. Finkelstein quipped that in 4 dimensions, it's basically 9/10 of the metric. And that's really where we start off in causal set theory. This is the hypothesis. It starts from this, it's motivated by this theorem and this way of thinking about spacetime as this poset plus this extra information. And the idea is to say, well, let's take that poset and quantize it. And this is what I'll refer to as the first quantization of in causal set theory, which is kinematic. It's not a dynamical quantization, it's kinematic quantization. And so the idea is that you discretize it. And in the process of discretizing, you actually put in this volume element that was missing. That was this, all you could say in the continuum is that two causal structure posets, when they're the same, the spacetimes are related via a conformal transformation. But now you're saying once you discretize it, the conformal factor is also hidden in that discretization. What I mean by that is that the idea here is that for a finite spacetime volume, and I will think of these two spacetime events and the causal interval that lies between these two events, and look at the number of fundamental spacetime atoms between them, and if that's finite, if this volume is finite, okay? And so that's the idea of discretization. So it's not, so one has to not get confused between discrete topology and this kind of discretization. This is more a local countability. So the definition of a causal set is that it's a locally finite poset. So in addition to acyclicity and transitivity, we also have the condition of local finiteness, which says that these Alexandrov intervals, which is this guy here, or this causal diamond, is got a finite, if it's a finite volume causal diamond, then it has a finite number of spacetime events in it. So in causal set theory, we basically want to think of discreteness as fundamental. So the continuum arises as an approximation. It's not itself fundamental. And so we have this way of thinking about continuum spacetimes as emergent, and that order plus number, and this is sort of the causal set slogan, that order, which is the poset order, plus the number, which is the counting, the local counting, gives you the continuum approximation, that is, gives you spacetime. And again, just to sort of give a historical context, there were many, I think that over several decades, people were thinking about such things. So one can attribute some of these ideas, in particular to Myrheim, who had a CERN preprint, which was thoroughly ignored, where many of the ideas were already present. But here's the actual hypothesis. Can you see my full screen? Because I'm not able to see my own full screen. Okay.
Yes, we can see.
Okay, great.
You are not on full screen. You are. We can see your background as well, just in case you're.
Oh, I see.
You can put it on. You can put it on presentation if you prefer.
Okay.
It's fine.
I had it, but I'm going to actually try to do a stop share and then do this again. Sorry, just because that's slightly annoying. So is this still, yeah, is this okay?
Yeah, that's good, yeah.
Okay, all right, great.
Could I just ask a question?
Yeah, sure.
Can you incorporate global hyperbolicity in this approach, or is it already there?
So I mean, it's not, so we're talking about all possible spacetimes, if you like, and discretizing all possible spacetime, and then some, and then things that are not spacetimes. So as long as they're causal, they're included. So future and past distinguishing spacetimes are very general, and globally hyperbolic spacetime is definitely future and past distinguishing. So it's included in this theorem, and therefore it's included in sort of our attempt to get at spacetimes which are, all possible spacetimes which are causal. So they're all included, but global hyperbolicity is a higher level, sort of a more stringent causality condition. So it's, yes, I mean, we would be able to get globally hyperbolic spacetimes, but there's a caveat there, which I'll try to explain a little bit down the line.
So you don't necessarily
what
have
we mean.
Yeah, you don't have a Cauchy surface then, which is the same question.
Right. So that's so if you think about it like that, you don't have Cauchy hypersurfaces in the same way. We can construct spatial hypersurfaces, but they're not Cauchy in the sense that they don't capture all the information that you need to define, say, an initial value problem at the discreteness scale. But nevertheless, if you borrow information, the causal structure information from a neighborhood, you can construct a lot more. You can, get out a spatial metric. You can do all sorts of things. So,
yeah, but the Cauchy surface is not a local concept, it's global. I mean, you can be locally Cauchy, but not global, and then you don't have a Cauchy surface.
Right. So I mean, I don't know how to answer this in a quick way, but I just want to say that if I have a spacetime that's globally hyperbolic, and I discretize it in the way that I will explain in a second to get an ensemble of causal sets, that's perfectly possible. So in this sense, it doesn't interfere.
Yeah. Okay. Yeah.
It has no problem. So we don't have a problem with global hyperbolicity. But if you want to intrinsically define global hyperbolicity in the causal set, then you run into problems.
Yeah.
Not that there are no approximations. So everything, all possible causal spacetimes are included, can be handled, so to speak. Yeah.
Okay. Thanks.
So so here's the hypothesis, which is that basically you take all your continuum spacetime,
just to go back, isn't global isn't the Cauchy surface related to the differential equation approach? So you need some sort of a continuum for to even talk about Cauchy surfaces. So it's,
well, I mean, it's true that Cauchy but you can define them purely causally, right? I mean, purely in terms of the causal structure, you can define. So one way of defining global hyperbolicity is to say that the Alexandrov intervals are compact. That's one equivalent way of talking about Cauchy hypersurfaces. The other one says that if you have a future time-like curve that goes through it once, then it can't go through it a second time. Things of that sort, which are completely, so it's true that the term global hyperbolicity refers to the differential equations in the way that they do in, flat space differential equation. But it's not, you can think of it purely from a causal structure point of view. Right. And so it's in the hierarchy of causal structures, it's one of those that are very stringent. So the requirement, we know that ADS doesn't have global hyperbolicity, right? I mean, stuff leaks out to the boundary all the time. So, but it's in the hierarchy of causal structures, it's one of the most stringent. And so the point here is that we can weaken it. I mean, this is what the theorem does, is weaken the conditions so much to make them, future and past distinguishable, which is a very, very weak condition. It's not exactly all the way to causality, but it's up to this point, and where it's it's almost violating causality, but not quite, right? So the theorem works for that. So then we expect that for such spacetimes, we should be able to recover everything relevant. So let me let me just so what is causal set hypothesis? The causal set hypothesis is basically saying that, you instead of the continuum spacetimes, if you want to think of the path integral and the continuum path integral over all possible spacetimes, 4-dimensional spacetimes, we throw that away and we say, actually what we have are these posets, all locally finite, partially ordered sets. That's the space. And so here are a set of examples of such causal sets. But of course, if we stop there, then it would just be any theory of causal sets. It would, which of course, you have Wolfram's recent causal set proposal, or for that matter, Lee Smolin and his collaborators have also theories of causal sets, energetic causal sets. If you stopped here, then that would be it. But we want to go back to where this was motivated from. We want to go back to the root of this idea, and that is to make the continuum correspondence. And that requires then this second part, which is very, very essential to how we think of causal set theory, which is that we really take this order and number correspondence seriously, where the order relation corresponds to the causal relation and the number to the volume. So if I have a spacetime, a continuum spacetime, I wanted to discretize it, I want to make sure that that discrete structure, that if there are events in the spacetime which I keep in the discretization, then the causal order there is reflected as an order relation in the poset, but also that I have a way in which I can make a correspondence between number, which is the local counting, and the volume, the spacetime volume. And if you did this using a regular lattice, we know that that would not be covariantly a good way of doing things, because the number of elements in a particular region is not covariantly defined. So a good way of doing this, and as far as we know, the only way that works, but although there may be better processes, this is an open question, but we do this discretization via Poisson sprinkling. In this process, so we have V is the space-time volume region. So it's a covariantly defined, so it's a uniform distribution in the space-time. And this is the probability. So that on average, so the number to volume correspondence works on average. So that's sort of the quote unquote compromise you make. You don't have a single lattice, regular lattice. What you have is a random graph, which has certain properties, which I will describe in a second. And that is that, yes, okay. So one very important thing here is that one thing that people worry about a lot is that if you're discretizing a theory, is it compatible with Lorenz invariance? And this is sort of a theorem that essentially says that it is compatible. So what is it that you want to ask? You want, so again, I want just think about a Riemannian, like Euclidean space, a plane, and you've got a random a Poisson distribution of points on it. That's the way you discretize it. Given a particular realization of that Poisson distribution, you can pick a direction in that, and that direction will transform in the right way in the when you rotate it, because this has to be invariant under the Euclidean group and so on, the two-dimensional Euclidean group. What happens in the causal set, because of the fact that we have invariant hyperbolae which are non-compact, if you picked a direction, you picked a unit future directed, say, along one of these green hyperbolae, then that direction, if you want it to really make sense, has to transform correctly under a Lorenz transformation to another sprinkling. And when you do that, you realize that you can attribute a measure on the space of directions. And when you do, that measure has to be uniform. And then that leads to violation of basically the fact that the measure has to be, sum to 1, because you have a non-compact space. And this is essentially the heart of this argument. We can discuss this later, but essentially it's telling you that even though you have a discrete space, a discretization of space-time, you cannot pick preferred directions. So you fundamentally, this Poisson distribution, and this is one of the nice features about the Poisson distribution, which I think is possibly, I mean, so which makes it even more important that what we've picked is a Poisson distribution. Whether other distributions also satisfy this, I do not know, but this is something that we can see is in fact the case with the Poisson distribution. So one question that you would want to ask is, does the causal set capture? Because I mean, you've discretized the space-time, so you've gotten rid of a lot of information. Does it capture enough information about the space-time? You know, we don't look for continuum limits really, except to sort of check with things. The density of sprinkling is always finite. And we have this additional feature, which is very special, which is that of non-locality. The graph that you get out is one which has not a fixed valency. For example, if you looked at the causal sets that are sprinkled onto Minkowski spacetime, then the nearest set of neighbors. So when I say valency, I just mean the nearest neighbors. There's an infinite number of nearest neighbors. So it's not as simple as a nice regular lattice. It's random. And moreover, it has this feature about valency. So the number of nearest neighbors can go to infinity. And this is actually just because of the fact that it has this beautiful Lorenz invariance built in, because we know that about the invariant hyperbole. They just extend out to infinity. So we also have a kinematic ensemble. So without actually going to real quantization, which is quantum dynamics, we have an ensemble of causal sets which represents the continuum, and you have to ask the question, how much of the information of the continuum can you recover just from order? And this is sort of what I call geometric reconstruction. And it's related to what's called the fundamental conjecture of causal set theory, where you want to basically say that a causal set, you know, it has order and number, and if it's something that comes from one spacetime as well as another spacetime, then those two spacetimes are really match up to the scales of the discretization. So, you know, below those scales they can differ, but up to that scale, they mean at that scale and beyond, they're going to be the same manifold. So they're approximately equivalent. So this, of course, is still a conjecture. There's been a lot of work in that direction, but I won't say anything about it today. So there are many topological and geometric invariants. I've just listed them here that we can just, you know, read off from the causal set. As time-like distance, they're dimension estimators. And for lack of time, I will focus on one that has been very, very important to the program, which is the discrete Einstein-Hilbert action. And this was work done by Benincasa and Dauker, followed with Dauker and Glasser. So Benincasa and Dauker did it for 2 and 4 dimensions, and Dauker and Glasser generalized it to arbitrary dimensions. And Glasser also did some work on calculating coefficients. So
I have some
really what you're, yeah, sure, please, yeah.
There is you try to incorporate causality in terms of order, causal order. But there is another concept, which is called Einstein causality, which basically tells the independence of states you can specify on causally complementary regions. Okay? In algebraic quantum field theory, this is very important. Here, I don't see what are the observables and what are the states.
Right, because I haven't started to talk about quantum theory yet. So let me come to that point and we can talk. I mean, so it's a very good question, but we have to, in fact, there's sort of some things we really don't know how to do. And so, but at this level, all I'm talking about is kinematics. I'm just trying to say, if you were to throw away the continuum and you want to construct a theory of causal sets, then you use some of this continuum discrete information correspondence to construct that theory. And the action is obviously something you would want to have if you wanted to do a causal set partition function. So we'd want to start with constructing that causal set partition function and then ask questions about that causal set partition function. So, so I'll come back to your question, Bal, but a little later. Yeah.
Okay, sure.
because we're not yet at quantum theory, and what you're asking is, of course, a difficult question because we don't have the answers to that direct, in some explicit way. But so I'll spend a few minutes on this because it'll kind of come up in the next part of the talk. So here we have the Einstein-Hilbert action, so you can see that, can you see my pointer? Yes. So you can see that in the limit of infinite density, you get the Einstein-Hilbert action plus some boundary terms. But what is this object? It's made up of these funny terms here, which are all obtained by counting. So give me a finite causal set, and I construct for you an action from it by counting various order theoretic objects in that causal set. Okay. So capital N here is the number of elements. Okay, it's finite. And then I count the number of nearest neighbors. N0 is the number of nearest neighbors. Okay, so there's no intervening element between them. Another way of putting it is that that's an Alexandrov interval of 0 volume. And then I count the ones with 1 volume, which look like this. Then I count the ones with 2 volumes, which look like this. There are 2 types, one like this and one like this, depending on how I arrange the elements in between, and so on and so forth. So all I'm doing is counting and doing this alternating sum with these particular special coefficients, which are fairly complicated in general to find. But this constructs for me the action just by counting Alexandrov intervals of different volumes in the causal set. Okay, and it's actually in some ways extremely beautiful because Alexandrov intervals, these causal diamonds, are something that we know appear even in the continuum case. Alexandrov intervals topologize strongly causal spacetimes, etc. They're the same as a manifold topology when the spacetime is strongly causal. So it's a very nice construction. And it's a very nice result that all you have to do is count these objects, and you've got the you've got the equivalent of the Einstein-Hilbert action, which when you look at spacetimes, when you look at the limit of infinite density, then you find that it's the same as the Einstein-Hilbert action. Okay, so let me come to the main part of the talk, which is what is a quantum causal set? And as I said, this is definitely a work in progress. We don't really know what we mean by the full quantum theory of causal sets, but there are broadly 2 approaches. One is considered, we think of as a more fundamental sort of bottom-up approach, which is quantum and the sequential growth paradigm. And so the idea is to look for a quantum sequential growth. And the other is more something that might be more familiar to most people, which is that you take a partition function, you try to construct basically the path integral, but here, of course, you're summing over causal sets. And even here, there are 2 ways of thinking about it. The one way that you can work on this is to consider state sum models where you do analytic continuation of a parameter, and you basically then have something that you can do Monte Carlo simulations with and study those. And this is work that Denjo participated in very actively for a couple of years. And more recently, this work, which I will begin talking about now, which is trying to understand how to deal with the entropy from with these non-manifold like causal sets, and sort of triggered by some very nice work of Carlip and Loomis and Carlip, which I will now talk about. So if I write down the partition function for causal set theory, I'm summing over all possible causal sets over some sample space of causal sets. I could pick that to be the set of all countable posets, or I could fix it to be some set of all finite posets. And of course, in the limit of n becoming very large, then it will go over to the set of countable posets. I could consider sparse finite posets, which is what I would do in the sequential growth paradigm. So things that have if I look at the past of any element, then that past is a finite set, which is of course not true in Minkowski spacetime, which past of every element is infinite, of infinite volume. Or I could dimensionally restrict the posets in some particular order theoretic way, which is what we do in the state sum models. And then, of course, you have the choice of the causal set action, and the natural choice is the Benincasa-Dauper-Glasser action, which is a discrete Einstein-Hilbert action. We could have other order theoretic actions like the link action, which is something that we do use, partly for convenience, but as I will describe, also it's justified in the particular context. Okay, so let's ask the question, if you look at this, if you look at the set of finite, if the sample space is a set of finite n element causal sets, and n is getting larger and larger, what does a typical causal set look like? Because you have the partition function and you're summing, you're weighting every thing with the e to the I s of c upon h bar, but you also have to worry about how many, what is the entropic contributions from certain classes of causal sets. And there is this very old result due to Kleitman and Rothschild that it's dominated by what are now called Kleitman-Rothschild posets, highly dominated. So they're basically drowned out. They drown out everything because it's super exponential and they grow super exponentially. So the space of causal sets, therefore, as n becomes larger and larger, grows super exponentially. And these causal sets have, as I've shown here, as a sort of, have three moments of time. You have an initial time, time in the middle, and then a final time. So they're very, very non-manifold-like, and they absolutely dominate the space of all n-element causal sets. And they have the property that, there are certain other properties that every element here is related to every element here, but the links are alive between the first layer and the middle layer and the other way around. I will go over the particular properties of these causal sets in a bit. But apart from this, so you have to worry about this entropy, but there are subdominant terms, which is what Dhar and Deepak Dhar found in a couple of papers that he wrote, and there was sort of these very nice work on phase transitions. If you just look at the order parameter as being the number of relations, and there are phase transitions which take you from layer to layer. So there are these highly layered posets. And why they're not at all like spacetime is because in this layered poset, which every layer is an anti-chain, which is a set of unrelated elements, every element here can be linked to certain elements in the middle, but it is related to every element that is 2 layers away. Okay, and if you recall the way I described what a manifold-like causal set looks like, it has this crazy valency, right? I mean, it can reach out really far high up the light cone, and so these are very, very non-manifold-like. So what you're seeing is that these subdominant things are also non-manifold-like. So basically, you have this set of layered posets which absolutely dominate the space of all possible causal sets. And you have to ask the question, well, how good can if you want to talk about the partition function, how well can your action do to deal with this entropic part, right? Sorry, I think I'm losing power somewhere. Okay, good. Okay. So that's the question that, in fact, so the one way of asking that question is to say, let's look at the partition function and divide it up into things of the layered posets and the ones that are not, and ask, well, let's just look at the contribution from those layered posets and ask whether the Benincasa-Dauper-Glasser action is sufficient to suppress this contribution. Because ultimately you do want to be able to, even if in the deep quantum regime you have these weird things that don't look like spacetime, you would like there to be some limit in which spacetime emerges, right? You need there to be some limit in which spacetime emerges. So this work of, I should have actually switched it around, Loomis and Carlip, was to talk, they dealt with the next subleading contribution, which is of bilayer posets. And when you look at a bilayer poset, so you have a set of completely unrelated elements, another set of completely unrelated elements, and the only relations you can have, therefore, are nearest neighbors. Okay, so only links are there, and that simplifies your Benincasa-Dowker-Glaser action enormously, because you don't anymore have to look for intervals of different sizes. You just have, you just have 0 element intervals. And so what you essentially have is a link action. So they looked at the simplest set. It's not the most dominant, but it's the next subdominant contribution. And if you look at, if you sort of look at the number of links and the number of possible links you could have, the number of possible relations on n elements is obviously n choose 2. And so you write down the number of links as some fraction of the total number of possible links that you could have. And I think what was nice that they did, I mean, was just notice that, of course, if you take n to be very large, this sum, which we think of as somehow more manipulable than an integral, can be converted into an integral, and we can actually study that integral. And when you do that, if you look at the class CPN of all bilayered posets with a given fractional set of links, which is P, then you obviously can rewrite your partition function over all bilayers as this integral from 0 to 1 of dp with this weight, which is the number of, this is basically counting that you have to do, the number of bilayer posets with P n0 links, weighted, of course, by what's effectively the link action, the exponential is upon the link action. Yes, so this is what they set out to calculate. And so the whole work is in actually counting the number of these posets. And they did that by looking at a subset of this set CPN by fixing the filling fraction, the filling fraction. So how many elements you have in a given layer. So the total number is n, which you say you have q in the first layer and 1 minus q, so qn and 1 minus qn in the second layer. And you can then just ask, well, given a fixed q, fixed filling fraction q, how many posets are there? And this is just simple combinatorics, like so. And you notice that the maximum, you maximize this counting when you have a filling fraction which is equal number on the bottom and equal number on the top, because the q into 1 minus q maximizes at that value. So what they did was to then do these very smart bounds to estimate to leading order, because everything here is to leading order. It's a large N approximation, and to leading order they estimated using just this q equal to half configuration. And so to cut a long story short, what you have, you could reduce it down to the partition function reduces down to this integral, where you have this imaginary piece here, and you have another piece which is an entropy function. It's actually just like an entropy function you would see anywhere else. And that's exactly this competition between the entropy and the action that you're trying to gauge. And what they found is that you can do a saddle point approximation. It's a little, not terribly difficult, but it's also a little subtle. And in the process, you find that there is, in fact, a regime in which of the constants that appear in the action for which there is a suppression. In D equal to 4, this means that the discretization scale is 1.452 of the Planck scale. So if you translate it into that. So in fact, what's really nice about this is that it tells you that the link action, or really the whole Benincasa-Darker-Glaser action, can suppress this entire, so up to this, in this large N limit, up to the saddle point approximation, it's basically suppressing the contribution. So of course, the question that we had to ask was, well, I mean, this is very nice, but what about KR orders? And we started off just looking and trying to understand this paper of Loomis and Carlip, trying to see which part of their counting arguments we could perhaps reproduce. And of course, once you come to 3-layer orders, we are stuck because we can't ignore things that are intervals of non-zero size, because the Benincasa-Darker-Glaser action includes all such, all such intervals, and they're all present. So, but if I look at the Kleitman-Rothschild, then, and here's the more detail on what they are really, these posets. Not only are they 3-layer, the ones that are dominant have the property that layer 1 and layer 3, basically the filling fraction is 1/4, whereas the middle layer, the filling fraction is 1/2. Moreover, and these are all combinatorial arguments, these are all coming from the Kleitman-Rothschild results, and that every element in layer 1 is related to half the elements in layer 2. And similarly, every element in layer 3 is related to half the elements in layer 2. So basically, you have links only between adjacent layers, and you have the number of elements, the number of links, the number of nearest neighbors goes like n²/8. And in this class of posets, numerically, we find, if you just calculate numerically what the 1-element intervals, for example, are, and they're really subleading, absolutely subleading order. In fact, this is a calculation that we have subsequently been working on, which I will also tell you a little bit about. So what we did, we were opportunists, and we decided that, okay, this is a very difficult calculation if we're going to actually incorporate the full Benincasa-Darker action, because then you have to look at iso-action causal sets and be able to count causal sets with the same action, and that would have been the weight that we'd have to, or the entropic factor that we'd have to use to play with the action, to sort of where the action and the entropy are, fighting against or competing against each other. So what we did was we said, let's just try the link action, because at some level, the link action is a very basic action. It's order theoretically perhaps the simplest action you could pick, which is just counting the number of nearest neighbors that you have in a finite causal set. And so we used the link action, and the counting, of course, also became significantly more complicated. And in the process, I think also one of the bounds in the paper, we understood it better in Loomis and Carlip's paper by thinking along these lines. So we had to define different kinds, and this is sort of perhaps too technical, but just to give you a sense that these are different classes of posets that one had to look at, different definitions of posets, and then to use bounds which were very similar to what Loomis and Carlip used, but now for K layers. And of course, the maximum number of elements now depends on this, maximum number of links, depends on the filling fraction in this way. And you have to look for the filling fraction that maximizes this alpha, which is basically this Q1, Q2 plus Q2, Q3. And when you do that and you write down the bounds and so on and so forth, you have a very, very similar calculation that pops out. And what is really surprising, and I think I didn't believe it for a while, so kept going back to trying to understand whether we had done something, we'd fudged something in the process of our calculation, but you basically get the same partition function. So we didn't have to do this saddle point approximation again. We just had the same partition function for 3-layer posets that they had for the bilayers. And so therefore, even for the KR posets, what we find is that this action, this link action is actually enough to suppress the KR entropy. And in trying to understand why it works for both the bilayers as well as the KR orders, we realize that the maximization of the links that happens when Q, the filling fraction, is of this form, and it includes both the KR as well as the bilayer orders. So, the maximization problem has all of these, and it is those maximal, they're the ones that saturate the bound, and that's what we're using, because this is to leading order calculation this is leading order calculation. So, so this was very surprising, but this is essentially, what you get when you take the link action. So it's promising. It suggests that, that we don't have to give up when we look at these highly dominant entropic posets, that maybe judicious choice of an action can help you get things that are, at least as far as these layered posets are concerned, will suppress them. But of course, the question that was always on our minds as well is, a link action enough? And can we somehow try to do this counting by taking the full Benincasa-Dowker action? And this is work in progress. These so the Carlip and Surya. So that's Peter Carlip, who is Steve Carlip's son, who got interested in the problem. And so the very nice counting problem. And so that's how we started to think about this. And here, of course, we have to ask the question, in this 3-layer case, and how do we count the number of R element intervals? Okay. So the way to do it is to start with the link matrix. And now I'm just going to allow there to be links even between level 1 and level 3, just to make sure that I'm not, just only looking at KR posets. I'm just looking at everything. And the link matrix is telling me, between element X and element Y, is there a link? If there is a link, that's 1. If there's no link, it's 0. Okay, so it's just the zeros and ones. And I think I need, because I want to calculate probabilities, I need to say with what probability any one of these link matrices between level 1 and level 2, or level 2 and level 3, whether what the probability for a particular element in that matrix to be 1. And I assign that some P. And as you can see, if I just take the square of the link matrix, I will be able to get all that I need in the case of 3 layers. Because as soon as the number of L squared ij is equal to R, means that the interval, that Alexandrov interval, has so many elements, R minus 1 elements in it. Sorry, maybe that should be R. I think I've ended up confusing myself. Anyway, yes, that should have just been R. And so if I then look at this matrix, and I see that I have the probability, all of these are just zeros and ones, these matrices. So if I have R, if L squared ij is R, then that means only R of these terms have both entries to be 1, right? Because they're just made up of zeros and ones. And so the counting becomes really easy, and you can find the probability for an interval to be an R element interval just by very simple combinatorics. And then therefore the probability for there to be n R element intervals, as long as R is greater than 1, or maybe I meant 0. Sorry, I've just, since this work is new, I mean, my notation is constantly shifting. I might have made an error here. But this is the probability for there to be that many NR R element intervals, okay? So there's just simple combinatorics. I haven't done anything spectacular here. But now I'm interested in the asymptotics. And what's important here, and here you, irrespective of what probabilities you've assigned for these link matrices, I mean, you might imagine that the right way to assign them is for P to be half, for it to be 0, 1. But let's just leave that aside and let it be anything. You notice that because of the fact that R, we're interested in intervals of size which are much smaller than n. So this is dominated by Q2n. And because the probabilities are less than 1, this object here is extremely small, right? 1, because it's to the power of n. So using that fact alone, you can simplify and calculate the probability for there to be nr number of these Alexandrov intervals of size r. And in the large n limit, it comes to look like this. Okay, so you can see that there is a suppression of the probability, irrespective of what you started off with. This is highly suppressed. And it goes like minus something times n squared. And that minus comes precisely because this object is less than 1. So when you take the logarithm of that, of the norm of that, it's basically a negative number. Sorry, you take the logarithm of that, that's a negative number. And so that's what one has done here. So what we find, therefore, is that it's actually fine to take the link action that in the three layer posets, we didn't actually lose out at all by not considering the full Benincasa-Darker-Glasser action, because they would contribute to subleading order to the saddle point. So really what our calculation now is therefore in firmer footing, and we can say that essentially the Benincasa-Darker-Glasser action suppresses this highly dominant entropic action. Of course, the next thing that you want to do is to see what happens to the subdominant, next subdominant ones, which are higher order, higher layers. And this is something we're working on right now. And much of these calculations, at least in terms of probabilities, work out. But of course, one has to then look for the fact that the counting arguments become a little more complicated. And there are several questions which are, of course, something that we don't yet know how to answer. So at this point, I would say that yes, we have understood a little bit more about the fact that these dominant, entropically dominant posets are in fact not as important as, at least up to the saddle point approximation. To leading order, they don't play a role in the way that you might have expected. I think a lot of people sort of rang the death knell of the ideas in causal set theory, saying that, there's too much of non-manifold stuff. You can't deal with that entropy. But I think that these arguments are sufficiently strong to suggest that, in fact, we have a fighting chance, even if we look at the set of all n-element causal sets. I think, so Dindro, I'm actually very close to the end of the hour, and I'm wondering whether, I don't have to finish the talk. I mean, I can just stop and I can just sort of maybe spend another.
We are not in a rush. We are not in a rush like that. We are interested in hearing it.
Okay, great. So of course, this is my single slide of the state sum models, where, as I said, we introduce this beta here, which is an analytic continuation parameter, which takes you from a partition function, which is a quantum partition function, to a statistical partition function. But in the process, you don't change the Lorentzian character of what you're summing over. So you're still summing over causal sets, but now the weight has become a statistical weight. And when you do this, you're able to, you take this object and put it on the computer, do Monte Carlo simulations. And this was a bunch of things that we did with several people here, including very important finite size scaling analysis with Dindro and Lisa Glaser. And there were certain characteristics that come out in this first order phase transition. And importantly here, I forgot to mention, is that we do a kind of dimensional restriction. So causal set theory, omega n, which is a sample space of all possible causal sets, or n element causal sets, includes all possible spacetimes of all possible dimensions as well. So it's a very ambitious program in that sense. So the idea here was to say, well, let's just look at a dimensionally reduced set of causal sets and then try to analyze what we can do with this. You put in the Bennen-Casadar-Glaser action and study these systems. And so it's a state sum model. And we found that in many of these dimensions, basically in 2 dimensions, but with different topologies in 2 dimensions, as well as in 3 dimensions, that there is this thing that looks like a phase transition. I've just sort of shown you in the 2D causal diamond, the 2 different phases in the cylinder spacetime, as well as the spacetime with a hypersurface, which is like a torus. When I say that, I just mean that these are things that are kind of like spacetime, but they're. So when I say topology, I mean it in a very general sense. Okay, so we did in the 2D case, we also did a very nice Hartle-Hawking kind of calculation. We calculated the wave function for the wave function of the universe, 2D universe, and we found some interesting features there. Again, where the wave function is peaked on certain geometries, which are very similar to those reflected in the space transition. So that's all I'm going to say here, because one of the things that we don't know in these state sum models, I mean, they're very interesting models. They're interesting because they also reflect the state of the art, so to speak, in a lot of approaches to quantum gravity, where this is what you do. I mean, in that case, you even analytically continue also your sample space. Here we don't do that. It's still a statistical theory of causal sets, but extracting what we mean by quantum causal sets, something quite, something unclear to us at this moment. So that's why I didn't think I should spend too much time on this approach in this talk. So let me come to a very different way of thinking about it. So far we've just been talking about partition function, things that we're familiar with from field theory, which a lot of approaches of quantum gravity start off with a partition function, especially those which are path integral inspired. But here's a completely different, as Monty Python would say, right? Now for something completely different, the sequential growth paradigm. And this was something that Rideout and Sorkin from very early on, many years ago, I guess 21 years ago now, worked on this sequential growth paradigm in the classical context. And the idea is that essentially think about dynamics in a completely different way than we've thought about before, which is that think of causal sets growing element by element. So there's a growth process by which space-time is created. And it's a very visually appealing way of thinking about time progressing by new elements being added and so on, but in a way that doesn't actually invoke, that only invokes causality. So it's a causal evolution. So elements are added to the future or unrelated to existing elements. So if you started off with this element here, then you can either add the new element, which is the blue element, which is unrelated to the first one, or add it to the future, and so on and so forth. Different ways in which you can add things. And this grows causal sets, which are labeled by the time in which the element came in. So there are all these colored elements, they're each of them different. But really what you want to extract from this is information about things that are colorless, or all the same color. So in the process, in the second leg of this, I generated 3 posets, which are really one and the same if I remove the color. They're all the same objects. I would like to make sure that my growth process is covariant. So the probabilities, these are still classical sequential growth, don't care about where they came from, the particular path. They're path independent. So putting all of this together, they came up with these models, which are characterized by a set of coupling constants, T1, T2, etc. And a way to think about it is in terms of this Qn, which is also related to the Tn, which is the probability that at any stage n of the growth process, an element is unrelated. The new element that is born is unrelated to everything else. Okay, so that takes a special place here. So they studied these, and there's some really nice work by Dindro and Xavier and Rideout and Sokin, where they talked about how these coupling constants actually renormalize. If you think of the universe going through bounces, then the bounce actually renormalizes a coupling constant, and they found fairly good evidence to show that the fixed point of this renormalization of coupling constants looks like the simplest thing you could get, which is the process of transitive percolation. Transitive percolation, you just have probability, let me write it down here, P for, so Q for this, and 1 minus Q for this, and so on and so forth. And so this also continues to be Q squared because the new element is unrelated to, two of the elements, etc. So you just have, the same, you just have one parameter. And so all of these multiple parameters sort of renormalize, and you get, and so there's evidence to show that, I mean, there are technical questions there as well, which I think nobody's fully sorted out, but it's a very, very evocative picture of how coupling constants can do a cosmological renormalization and come to a fixed point. One of the things, and this becomes relevant to quantization, is that a nice way of thinking about this, because these are stochastic growth processes, is as a measure space where you have the sample space. And in this case, these are past finite causal sets because they've all started off from a single element. So at any stage of the growth, any element will have only a finite size past. And so omega is a set of all past finite posets. And this script A, this math frac A, is the event algebra, which is constructed out of so-called cylinder sets, which are basically generated by the finite time events. So this, and it's very similar, the whole construction is very similar to the random walk. If you were to construct the random walk as a measure space, then you think of the random walk up to point this, and it can be anything beyond that. And that is your cylinder set, where you've only specified the first n elements, and so on and so forth. Dindro is, of course, very familiar with this because he's worked on this for the quantum measure. So these cylinder sets basically generate your event algebra, and the space that you generate are all of labeled causal sets. But I said that we need to look at unlabeled ones because those are covariant events. And so what we need actually is to go to the full event algebra and to extend this measure, which is defined on these on this finite event algebra, and extend it to infinite time, so to speak, to this full sigma algebra. And that's the only way in which you can define covariant events. So covariant observables in this, so this is in fact the Carathéodory-Hahn extension theorem, which says that any classical measure, any probability measure will extend from a finitely generated algebra to the infinite one, which is where you can construct covariant events. So what are these covariant observables or events? They're the sets, they're in this event algebra which is generated, they're the sets which are invariant under relabeling of the causal sets that make it up. And examples of these are, so essentially you want something that doesn't have labeling on it, and it's the set of things which has, so let me just to clarify, if I had this originary event is one where I look at all possible causal sets, which have one element to the past of everything else. Okay, that's just a set of causal sets. And that's invariantly defined. It's covariantly defined because it doesn't care about the label. That set is an observable in the sense of a, I mean, in the word, in the way the Bell looked at it, it's a beable. And I can assign a measure to that set. These are the measurable sets. So covariant observables are measurable sets, and they're covariant measurable sets in my theory. And that's it. So I can say, well, what is the probability for this particular thing to happen, right? I can assign the probability for there to be an originary event. And in the classical case, I definitely have a reasonable interpretation of this. So there are also analogs of past sets, which are stem sets. I'm not going to say anything about that, but just end with some remarks on how do we quantize this system. In this quantum system of trying to think of quantization of a stochastic theory is a very different kind of quantization than you're used to, thinking in terms of Hilbert spaces and states and so on and so forth. What you do is you take a classical measure space. So you have omega, you have the event algebra, and you have the classical measure, which is the probability measure. But all you do in this quantization is to replace a classical measure with what's called a quantum measure, or equivalently a decoherence function. And the object that we deal with is called a vector measure. So it takes values in a Hilbert space. And that Hilbert space actually secretly comes from a histories Hilbert space, where you've taken the space of histories, done a GNS construction, using the decoherence functional as an inner product, and constructed a Hilbert space from it. And this vector measure takes values in that Hilbert space. This technology is not something that people use very much, but it's the way in which we think is most suitable for dealing with quantum sequential growth. So all you do is you still have the same sample space, you still have the same event algebra, but now your measure is a vector measure. But of course, you have to ask the question. We started off with this, labeled causal sets, things which are not covariant. And the only way you get covariance is to go from a finitely generated algebra to the sigma algebra. And with that, in that process, the measure also has to extend. You have to carry that measure with you. So it also can extend to the sigma algebra. Otherwise, you can't define covariant beables or covariant observables, you don't have measurable sets, which are covariant. So what happens with, vector measures, and this is something we realize is this theorem due to Carathéodory, Hahn, and Kluvnik, which states that you really need to satisfy certain convergence conditions. It's not a done deal. It's not like the classical probability measure that all vector measures extend. And in fact, and so here I've talked about this histories Hilbert space. Dinjo and Xavier and Raphael did some really nice work on the quantum random walk. And in that process, they discussed this, and it was later sort of fleshed out in great detail by Darker, Johnston, and Sorkin. So in the quantum sequential growth, so what is the quantum sequential growth? Then you want to be able to write things in terms of these vector measures. And the simplest case that, and in fact, I should have actually written this right at the start, which is that the simplest thing that you might want to do, because we had these probabilities, the Qs and so on, which took values from 0 to 1, right? But now you can say, well, let's just complexify it. So that's the simplest class of models you can think about. And this is really as far as we understand. So this is the state of the art, if you like. We just know how to deal with the one-dimensional Hilbert space of causal sets. And here, you've just complexified. And your Hilbert space then is just the 1D complex plane. And what the process of growth does is it acts like it's an operator of this sort. And it basically takes you from one vector to another in that Hilbert space. You start off with one vector, start off with sort of the universal vector, and then it sort of, as you go up the path, it takes you along to another vector. And that's the growth process. We aren't able to implement this. I didn't talk about it, but this is sort of a causality condition, which may be related to what Val was talking about, which is really to do with entanglement. Here, these are causal, things that are evolving, but you want to ask the question whether the state is entangled with things that are space-like related to it. We don't know how to implement this kind of causality in this dynamics as yet. So whether that's something very important, I personally don't know how important this condition is. For us at this moment is to basically ask the question, can we even construct a dynamics? Because we're not guaranteed that your measure extends. So we're not guaranteed that you have a quantization that's actually covariant. And so one of the first things that we had done many years ago was to look at the case of complex percolation. Complex percolation, which is simply to take that one, take transitive percolation. So we have just one coupling constant and you complexify it. And for all stages, you have the same coupling constant. And when you do that, you find that this, so I've actually skipped a little bit. I wanted to say that the theorem simplifies to a very simple convergence condition when you have a one-dimensional Hilbert space, and that is that of bounded variation, which is essentially a collinearity condition on the measure, that it should basically converge in a collinear way. And what we found is that in the simplest case that we could think about, the measure does not extend. So you cannot define a covariant quantum sequential growth dynamics for such simple models. So it's interesting because the transitive percolation plays such an important role in the renormalization group thing. In the classical case, that's the fixed point. But here, what you might imagine to be a fixed point is actually not a well-defined theory. But very recently, I guess last year, we finally put out the work with Stav Zalel, who is a Fedaka student. We found a class of models, okay, more complicated class, but we found an entire large classes of models in which, in fact, the measure does extend. So in a sense, what we did was we proved existence, that it's not that every sequential growth dynamics that you construct is doomed to fail, even if it's in a one-dimensional Hilbert space. There exist such models. So what can you do with them? So one example of a covariant observable that you can construct is that of originary growth. What's the probability? What's the measure for originary growth? And even though we don't have a full interpretation of what a quantum measure is, you can definitely state the following, that if the measure is 0, then that thing does not happen. And so we have explicit examples of an observable that's predictive for this particular model, saying that if the coupling constant is of this value in particular, if the first of the TIs is, or the second of the TIs is 0, then the originary event does not happen. So it's a predictive statement from a particular model of causal set quantum gravity, for whatever it's worth. So let me end here, and sort of my last slide. So what is a quantum causal set then? I think my understanding of what we want, we don't have a full theory of quantum causal set, quantum gravity. We're heading there in some little ways. We've got little windows of insight into certain things, but I think that if we want to think of a quantum causal set, it's really a covariant quantum measurable set of past finite causal sets. And that's exactly what I was saying, that, if that collection of causal sets, which represents an observable or something that is a covariant event, is to me what is quantum about it, because it incorporates dynamics via the measure. And that's what a quantum causal set is. And it replaces what we think of as a Hilbert, as a wave function. But what it is actually that measure that we have is a measure on a Hilbert space. But that measure corresponds to this particular observable. So it's not quite the way we think about wave functions, sort of this thing that, takes meaning when you take its expectation value of an observable with that. But it's something that, again, you have Hilbert spaces, but really what you have are observables or beables or measurable sets at the heart of it. And of course, when you're looking at the saddle point approximation, as we did in the partition function, again, it's very similar to how we would think of, paths in the path integral. Even in quantum mechanics, we think of the classical path with the stuff that surrounds it, the things that are the leading order corrections are the quantumness to it. And that's what I would think of as a quantum causal set as well. And we are, of course, a long way from understanding this. And there are these various questions. Can we construct more realistic quantum sequential growth, etc.? I'll just leave them out here. One, of course, is there a quantum renormalization of coupling constants? This is directed to Dinger, suggesting that maybe it's something to think about, and so on. So thank you very much for your attention.
Thank you very much, Sumati, for a very comprehensive tour through what's recent and new and exciting in causal set theory. And it's open to questions.
Can I ask?
Yes.
Sumati, you gave an excellent presentation. Actually, if you're too clear, it provokes questions. You realize that?
That's brilliant. That's all I want.
Okay. What do you mean by covariant? Is it under the Lorenz group?
No. So covariant, of course, so let me just sort of bring you away from causal sets. If we're just talking about spacetimes, suppose I was looking at, the path integral over all Lorentzian spacetimes, okay? 4-dimensional Lorentzian spacetimes. Then covariance there means really diffuse invariant, right? And diffuse invariance has the ability to, and I'm going to say something controversial here, so which has the ability, there's two ways of thinking about diffeomorphism. One is the poor person's version, which is just coordinate invariance. And the other is a more complex, very complex way of thinking about it in terms of, diffeomorphisms, leader derivatives, all of that, the whole, and I feel, so this is really the simplest way of thinking about diffeomorphisms, which is that you have these finite number of points, you can label them. I don't want to put any physical meaning to the labels. I only want to talk about objects that are unlabeled. So if I just go back to this, this slide here, I have this gray object here. These are the three different colorings that I could have. Sorry, I'm not pointing actually, but yeah, these are the three colorings I can have. And I treat them all as one object. So I treat them as an uncolored object because I don't want to label them. So that is a sign that the dynamics is covariant. I want to make sure that the probability for that process or this process or the other one is all the same. So covariance is, in some sense, in causal sets, we just have our notion of diffeomorphism is the poor person's version of diffeomorphism, which is coordinate invariance, which is you in any space-time.
Okay. Can I make a remark? Okay.
Yes.
In the context of algebraic quantum field theory, we talked about it. Okay. There is I also get the impression that the measurement, the algebras you are considering are finitely generated. That is, in some finite corresponds to some finite space-time regions. Okay, but never mind. But there is a very general theorem due to Kohn and Stoma, which says that, well, first there is this very strong result that local algebras in quantum field theory in the continuum are what they call type 3-1 von Neumann. Then Kohn-Stoma essentially says that every state on this algebra can be unitarily transformed arbitrarily near any other state. And the conclusion is local measurements can never be made. I mean, you cannot get any result out of local measurements because two states are not distinguished within an epsilon. Okay? I don't know how this impacts on this program.
Right. So I think at some level, it would be very interesting, I think, eventually, if we understood the full structure of our theory, because we understand it as a quantum measure space. We also know that from this work of Dowker, Johnston, and Sorkin, that in the case of quantum mechanics, the Hilbert space that you generate through history's Hilbert spaces has a canonical relationship to the original Hilbert space. Okay, so you can, in those cases, make a correspondence, but I think that we still don't understand fully how operators and, this language of observables and the standard way of thinking about it, and here how they correlate. So I think that it's an interesting question whether the finiteness. See, when I say this is an algebra, this is an event algebra. It's in the sense of measure space, right? An algebra which is closed under unions, finite unions, and finite intersections and complementation, right? Which has one of the elements is the full set and so on. This is the kind of algebra we're talking about. It's not a C-star algebra. On the other hand, having said that, I think that the structure of the theory, when we've just looked at a specific example of a one-dimensional Hilbert space. But in general, we could have, I think I would be very surprised if the full theory, full space was not, an infinite dimensional Hilbert space on which this measure lives. In which case, maybe if not directly, some of these questions might come into play. But of course, we also have to, you talked about measurement. We have this is a quantum theory of closed systems. That's something that I didn't mention, but we have no observations that are done from outside of the system. So the idea of putting a measure and interpreting that measure is, of course, something complicated. There's this co-event interpretation of Raphael's, which has come up with certain, how do I say it? Interesting features, possibly problematic features, but I don't want to even go there. All I want to say is that there's a much simpler interpretation, which of course is not complete, which is that if a set is of measure 0, then it doesn't happen. And that's all the level of observation that's important for me.
Okay.
Because I want to give it, there is no external observer, there is no projection operator. That paradigm is just not the one in which this quantum sequential growth is,
okay.
operating.
So that's what is puzzling me, because for epistemology, from what we perceive, there are, from the physical theories I know, except this causal set theory, one has first states which describe the measured system, and algebras which are possible attributes of what we can measure, and you get a number by joining the two. Okay, here I don't see that structure. In particular, even internally, there is no specification of what is the algebra is. At least I don't see it. What is the product of
right? No. So the algebra here is an event algebra. So that algebra is generated by. So if I have a measure space bulb,
It is unions.
Like, yeah, that's it.
That is
Those
not
are
an algebra.
unions and that is what is called an algebra, and
In probability, yes, I know. It is what is called an algebra in the probability theory, and I have had a feeling that that's not algebra. What is called algebra in people approaching this problem from sister algebras or say algebras of boundary operators? What is meant by algebra is not this union kind of union intersection algebra. They seem to be different uses of a language. Okay? So I am puzzled.
Yes, there is a strange usage here, and at some point I think I resolved it in my head some years ago why it's called this, but so it's just it can be mapped onto an algebraic structure, but it's definitely not a C-star algebra from what I know.
C-star is not so important. It should be an algebra.
I mean, the algebra is generated from these sets. You need to have a star operation of some kind. None of that is here. There is no equivalent, as far as I know. I mean, maybe if I thought about it, maybe something, I don't know, Ian, one could, but I don't see the analogy is, kind of distant. Okay. Having said that, if you have a Hilbert space, you basically have this thing that you have a vector in the Hilbert space. You start off with something, and what the growth process is doing is to take you in that Hilbert space. It's operating, okay? But these are like a transition, what are they called? Transition matrices. What's the standard way of thinking about it? These are things that take you from one state to another. These are not unitary processes, but they're transition amplitudes of some kind, which are taking you from one state to another. And that's what's happening. And you're mapping out some part of the Hilbert space in this process. Now, whether those operators, can we see them? We don't understand enough about that Hilbert space structure, I think, to say or to make the analogy with other things like the kinds of algebras you're talking about. But I think, so you can only speculate about the fact that there might be a relationship, but I think that the whole paradigm is very different. Having said all this, Bal, of course, we've also looked at, quantum fields on curved spacetime and on causal sets, and there, that algebraic structure is, also manifests itself.
So, problem is that, hello, can you hear me?
Yeah, I can hear you. Yes.
I don't understand what is the epistemology behind this. Okay, I mean, one can make mathematical theories, but one has to have some intervening theory about the epistemology, how it comes to us, okay, comes to human beings. Okay, this is not clear to me here. Okay, but you agree with that? You have to study. One has to study the problem better. But I want to know.
But I mean, if you want to talk about phenomenology, Bal, I mean, there is a lot of causal set phenomenology which I didn't talk about.
I'm not talking about
basically. There's even if you come to think about, even if you're talking about quantum fields on curved spacetime or quantum fields on causal sets, causal sets provide you with a certain kind of UV finiteness, which you can talk about, but at the fundamental level, you have to ask the question, what does it mean? I mean, this is like going back to things that people have been talking about for a long time. Bell and others have said, what does it mean to do measurement in a closed system? What does it mean to have measured something in the early universe? I mean, you have to have something. I mean, this is sort of the elephant in the room about quantum information, quantum interpretation. But people don't like to talk about it also because we don't know what to say. We really don't know what to say, but it's there. I think it's a huge gap in our understanding of quantum theory, that we don't know how to go beyond observables. And there's just absolutely no meaning in quantum cosmology that could be given to measurement. I mean, I feel very strongly about it, but I don't know what to do about it. So we work to the best of our ability around the really difficult question.
I am not sure I agree with you. At least now, I think a well-articulated, forget about Bell and so forth. Yeah? Bell well articulated process whereby a number, complex number is produced from states and observables. Okay, I think so. But regarding cosmology, I don't want to make a remark. Okay? Maybe it doesn't make sense to talk about wave function of the universe and stuff like that. But I don't know. I don't want to say anything. But I want to ask you, what do you mean by Bell causality?
So this is a sort of, I think, a choice of phrase that Raphael and David chose when decided on. It's essentially like, it's basically another way of thinking about it as spectator independence. So you have a process and you decide on whether the new element, you look at its precursor set, all the elements that it's going to be, are going to be to its past. And the probability for that should not depend on the presence of spectator elements. But of course, that's too naive a way of saying it. So things that don't participate in that transition. So you actually express it in terms of, there's two ways of doing it. One is as a product of things where you take, or as a ratio of two processes, and you say that you take two processes which have the same spectator set, and then two processes which have different spectator sets, and somehow the ratios of those two things should be the same. So it's a slightly technical point, but it's essentially to try to say that since it's a causal evolution and the new element comes and it's going to be the future of a set of elements, it's precursor set, it shouldn't matter what elements there are, which are not in its precursor set. It should only be determined by how many connections it makes to the set of things that it will make connections to.
Again,
So
in
it's
algebraic
just-
quantification theory, sorry, I know that I'm interfering, but if you have two space-like separated regions, call them O and O prime, okay, then if one gives a state on state, suppose you give me a state on O and O prime, that is, give me a state omega, that means it is mean values in A, O, and mean values in O prime. Okay? So it's a state on, now there is quite a rigorous theorem, okay, that one can change the restriction of this omega to O without, in any way you like, without affecting what is happening for the restriction of omega to O prime. Okay? This is a theorem, okay, and it comes from type 3-1 phenomenon algebras, and it has been reviewed by many people, including Ingvar Sound and so on. Okay, so that seems to answer your remark. Okay? I think so, because there is definitely causal independence of observations in space-like separated regions in the framework of algebraic quantum field theory. Okay? And I don't know how this comes here.
Yeah, I think that when you want to implement it in a quantum sense, this is what I was saying, that's the question of, entanglement is of course there. So it's not like classical probabilities. So here I'm talking about, in the slide is just classical probabilities. But when you have quantum entanglement, how does it exactly manifest itself in this way in the dynamics? Does it need to, or is it something that comes out? I, for one, don't have a good understanding of it. There are people, Johansen, of course, Raphael and Faye have thought a lot about this quantum Bell causality condition, but I have to admit that I don't have a good sense of whether it's needed or if it's something that if you just sort of blindly follow your nose and construct a theory, that you will get things like entanglement. I think entanglement is obviously there, but it's there because you have interference, you have all of this. That's the whole point of a quantum measure. But I don't know whether you need another extra condition like this.
Okay. Can you send me Milham's paper you mentioned in CERN?
Yes, I will look for it. It's a CERN preprint. It's a very nice little preprint.
I don't know. Okay.
We met him, we had, didn't you? You were there in Edinburgh for the meeting.
Yes.
No,
we had a causal set meeting, and Jan Milheim came to that meeting. He was a very quiet person,
Right,
and
I
he
think
said that when he tried to get the paper published, he ran into a lot of opposition. I mean, like people were just scoffed at him.
and the paper has never been published.
Never been published. It's a CERN preprint. And it has some amazing, I mean, like, if you looked at it and you thought, well, that's causal set theory for sure. But also, if you look at certain papers, like you go back to Penrose and Kraunheimer, and they have sort of, it's very prescient in some sense, because it's sort of many of these ideas of discreteness, of the poset structure being important and so on, are there in Finkelstein. So I feel like it's sort of been it's a culmination of many of those thoughts and ideas. But, yeah.
Okay. I think Ricardo wanted to ask a question, no?
No, thank you. Sorry.
Va bene.
We can stop the recording at this point, probably.
Okay, great, thank you.
Just
Okay, then.
we can continue.
All right. It was a very clear presentation. Very nice.
Yes,
Thank
absolutely.
you, thanks.
Thank you again for
Okay.
such a clear presentation.
We'll be in touch. Okay.
Thanks.
I
Yeah.
also will. Yeah.
Thanks a lot, Ginger. It was a pleasure.